Let's discuss determining the minimum sample size when estimating a proportion. Suppose we are about to draw a sample and we wish to estimate the population proportion p. We may wish to estimate p to within an amount m with 95% confidence. We may wish to estimate p to within 0.05 or 0.02 or within 0.001 or whatever we feel is appropriate in a given situation. And the question here is, how large of a sample size is required to achieve this? In almost all situations, sampling doesn't come without some sort of cost, in terms of time, money, or other resources. So we may want to determine the minimum sample size required to achieve our goals. Wanting to estimate the population proportion p to within m at a certain level of confidence is the same as wanting the margin of error to be no more than m. Here's the margin of error of a 95% confidence interval for the population proportion p, and we'd like this to be no more than m. In the general case, in situations like this, we simply solve for the sample size n. But we run into a bit of a problem here, as the sample proportion p hat appears in this formula, and we haven't drawn the sample yet, so we don't know the value of p hat, and we can't use it in the formula. So here I'm going to replace p hat with p star for the time being. P star represents an estimated value of the population proportion p. We'll discuss what value to use for p star in a moment or two. Now we need to isolate the sample size n. I'll let you work through the details of the algebra, but we'd isolate the sample size n by multiplying both sides by the square root of n, dividing both sides by the margin of error m, and then squaring both sides. We end up with this. To estimate p within m with 95% confidence, we would need a sample size of at least this many observations. To change the confidence level from 95% to something else, we change the z value. In the general case, to estimate p to within m with 1 minus alpha times 100% confidence, we need a sample size of at least this quantity. Z sub alpha over 2 is the usual z value for the given confidence level. 1.96 for a 95% confidence level, 1.645 for a 90% confidence level, etc. What value should we use for p star? There are two main options. We may have an estimate of p based on prior information. We may have other samples from the population or some past experience that gives us a reasonable ballpark estimate of p. But if we don't have a reasonable estimate of p, we should use a p star value of 0.5. This is a conservative or worst case approach and ensures that the sample size is large enough regardless of what the real value of p is. The quantity p star times 1 minus p star is greatest when p star is equal to 0.5. So the choice of p star of 0.5 results in the largest minimum sample size of any value of p star. I'll let you verify that for yourself. Let's work through a couple of examples. Suppose we wish to estimate the proportion of adults in Ontario that are in favor of harsher penalties for drug offenses. This proportion is the parameter p, and we're trying to estimate p. How large of a sample size is required if we wish to estimate p to within 0.03 with 95% confidence? Here's the sample size formula. The sample size must be at least this quantity. The z value corresponding to a 95% confidence level is 1.96. And we want to estimate p to within 0.03, so m is 0.03. And we square that quantity. What should we use for p star? Well, we appear to have no estimate of p to use in the formula. And if we have no reasonable estimate of p, we should use the conservative approach and choose a p star value of 0.5. So times 0.5 times 1 minus 0.5. If we carry out this calculation, we'd see that we need a sample size of at least 1,067.1 individuals. But the sample size must be a whole number. To find the minimum sample size required, we need to round up to the next largest integer, 1068. We would need a sample size of at least 1068 individuals in order to estimate P, the proportion of Ontario adults that are in favor of harsher penalties for drug offenses, to within 0.03 with 95% confidence. These sample size calculations are often used as a rough approximation to the sample size that is required. We don't necessarily run out and get a sample size of exactly 1068 people. We often see samples of about this size in political polls. Political polls are often based on a sample of about 1,000 individuals, with a reported 95% margin of error of about 0.03. Here's another example. Suppose we wish to estimate the proportion of mice that would be killed by a certain dose of a chemotherapy drug. Suppose also that previous studies have shown that approximately 10% of mice are killed by this dose of this drug. Suppose that we are feeling a little ambitious, and we wish to estimate P to within 0.001 with 99% confidence. How large of a sample size is required? Recall that we suspect from previous studies that P is approximately 0.1. Here's the sample size formula. We need a sample size of at least this quantity. For a 99% confidence level, to 3 decimal places, the Z value is 2.576. We can find that from software or a table. If we used software to find that value to more decimal places, we'd get a slightly different answer than we're going to get. But I'm just going to use 3 decimal places here. There will be a little bit of rounding error. We want to estimate P to within 0.001, so M is 0.001. And we square that quantity. What should we use for P star? Well, if we wanted to be conservative, we could again use 0.5. But previous studies have shown that P is approximately 0.1, so it's reasonable to use that value in this formula, times 0.1 times 1 minus 0.1. One could make an argument that we should still be conservative and use 0.5. But if we feel 0.1 is a reasonable estimate of P, there's probably no need to be that conservative. If we carry out this calculation, we'd see that we need a sample size of at least 597,219.8 mice. If we want the minimum sample size required, then we'd round up to the next largest integer. The minimum sample size is 597,220. So we'd have to conduct an experiment and administer the drug to almost 600,000 mice in order to estimate P to within 0.001 with 99% confidence. That brings up the point that the required sample size may not be reasonable, and it certainly isn't reasonable here. We're not going to go out and run an experiment with 600,000 mice just to estimate P to within 0.001. So we may have the desire to estimate P to within 0.001 with 99% confidence, but it's simply not possible from a practical viewpoint. We're going to have to adjust our study plans or even abandon them. What we wanted to show, we simply cannot show. Now let's look at a few plots to illustrate the effect of the desired margin of error and confidence level on the required sample size. In this first plot, I plotted the minimum required sample size against the desired 95% margin of error. I used the p-star value of 0.5, so this is an illustration of the values from the first example. In the first example, we had a desired margin of error of 0.03, and the minimum sample size required was 1,068. We needed to sample at least 1,068 people in order to estimate the population proportion to within 0.03. If we wanted to reduce the margin of error to 0.01, we'd have to increase the sample size to almost 10,000 people. This would cost a lot of money and time, so it's usually not worth the effort. The p-star value of 0.5 was the conservative or worst-case approach. If we were to use a different value of p-star, the minimum sample size would be less. To illustrate, suppose we let p star equal 0.3. This dashed curve is the resulting minimum sample size curve. We see that we need a little lower sample size if p star differs from 0.5. The sample size formula contains p star times 1 minus p star, so this curve would be the same if p star equals 0.3 or if p star equals 0.7. What happens if we increase the confidence level? These two green curves represent the minimum sample size required for a 99% margin of error. For a given margin of error, if we wish to have greater confidence, we need a greater sample size. If we want to estimate p to within 0.01 with 99% confidence, we need a sample size of over 16,000 individuals. Whatever the confidence level, the required sample size increases dramatically as the desired margin of error gets closer to zero. So in many practical situations, it may not be possible to pin down the value of p as precisely as we would like. And that's a brief introduction to sample size calculations for estimating a proportion.